Hey everybody, your Friendly Math Tutor here with another lecture video. We've got 2 left. So this is the last unit. This is a BC only unit, Unit 10 on infinite sequences and series. This is going to be another 2-parter. So today we're just going to go through a lot of just examples of how to solve infinite series. Essentially, sequences are related to that, but it's really just going to be focusing on all the different methods to solve infinite series. So let's jump in. So we start with geometric series. A geometric series is going to be anything that can be written of the form r times a to the n. Right? So this is the general format. I wrote that backwards. It's really a times r to the n, because r is the common ratio and a is going to be what we're going to call the first term. Now, if the geometric series converges, it's going to converge using this formula, a over 1 minus r. That again is only if and only if it converges. Now, how do we know if it converges or not? So let's take a look. We've got 4 examples. First of all, every one of these is of the form a times r to the n. It might not look like it, but we're going to either show that it is, this one is, this one is, this one not quite yet, and same thing, this one not quite yet. So we are going to write it as a times r to the n, and then we're also going to talk about how the number that's in this spot may or may not be the first term. There's going to be a surefire way to always find the first term, all right, because we're going to need that here. But the first thing to do is identify what r is. Here, we have a times r to the n, so r is a half. If r is between -1 and 1, this is what you look for. You want r to be between -1 and 1. That means that our series converges, meaning as we add the terms from the sequence forever, those values that we're adding tend towards some specific value. They kind of have a wall that they'll never reach and never go past, all right? That'll only happen in a geometric series if r is a number between -1 and 1. So if we look at this one, this means that since it's a half, and a half is between -1 and 1, this one will converge. So all we do is we use the formula. It'll converge to some infinite sum. Now A could be this number, or sometimes it might not be. It depends on the index down here and what our initial index is. So what I would do to, instead of worrying about that, just to always get A, just plug in the number that's down here. So if I plug in 0, anything to 0 is 1, and I do get 3, so it does happen to be this number. But if the index was something else, we'd be starting the series at a different value. So rather than talk about all the different cases, simply just plug this number in. That gives you the first value. 1 minus a half, that's our common ratio. This gives us a half. 3 divided by a half is 6. So that means if I add these numbers of the sequence together to create the series is the addition of the terms in the sequence, we'll approach 6. We'll get to like 5.9, 5.999, and so on, but we'll never reach 6, and certainly never go past 6. Let's jump over here to number 2. This is not quite in the format, so here's how I'm going to rewrite this. No, I'll leave that. We'll just do it this way. So I'm going to rewrite this. I'm going to bring the 3 in front, and then there's really a 1 over here. So I'm going to think of it as 1/4 to the n. So that's another way to do it. So some of them it'll be helpful to rewrite it, because there's an imaginary 1 up here, and 1 to the n is 1. So now I can clearly see the common ratio is 1/4. And if we use our formula, I'm going to get rid of this. So we've already kind of talked about that just to create some room. And here we got our formula. A A is actually not 3 like it was back in this one. This is why we're going over an example that looks similar. Our first index is at n equals 1. So when we plug in 1, 3 times a fourth is 3/4. So the first term in our series is actually 3/4 here. And then it's 1 minus 1/4. Well, what happens is 1 minus 1/4 is 3/4. So in this case, we get 1. All right, so we get a different answer depending on where we start, which should make sense because if you add an infinite number of terms together and it equals some value, if you get rid of the first term, it should equal, as if we're subtracting that value. All right, number 3. This one doesn't have a term here, but that doesn't really matter. This is our common ratio, and something I just took for granted here and I didn't mention was the 1/4 was between -1 and 1, so we go ahead with the formula because it converges. But this one, pi is bigger than 3.14. When you divide it by 3, you're going to get a number bigger than 1. So this one just diverges. Which means if we sum the terms in the sequence up, there is no wall. It just keeps going. It just grows without bound. And number 4, I'm going to rewrite this one. So a lot of the geometric problems are going to be rewriting. This 2 I'm going to put here. I'm going to swap the 2 with the -1. If I have -1 to the n and 3 to the n, I can write that as -1/3 all to the n. It's just some manipulation of exponential rules or exponent laws. So again, 2 may or may not be the first term. So when I use the formula, A represents the first term. I know right here I wrote this, but it depends on what the index is, whether or not A is actually the first term or not. It is the first term if n equals 0, which is like the standard. But here n equals 1. So I do -1/3 to the first is -1/3 times 2. So -2/3 is really the first term. And then 1 minus -1/3 would be 1 plus 1/3. That's 4/3, and -2/3 divided by 4/3. The 3's cancel, it's -2/4, so I get -1/2. And again, I skipped this part. I shouldn't be doing that. -1/3 is between -1 and 1, so it does converge. So if we take a look at geometric series, this is generally the type. There is another type called telescoping that we'll talk about, but for geometric is really the one type where you can actually find the sum. So it converges if r is between -1 and 1. And then you can find the sum using this formula. But what happens is most of the other series that we deal with, we don't have we don't have specific formulas to actually find the sum. What we're going to be concerned from here on out is essentially just, does this series converge or diverge? Not necessarily what it converges to. So if you have a problem that asks you what is the value that it converges to, that's typically a good hint that it is geometric because it's the one that we can actually find the value that it converges to. Okay. So now let's start to look at other types of series and different tests that we can use to figure out whether they converge or diverge. So one is called the nth term test, and a lot of times it's really just the nth term test for divergence because that's all it's going to tell us. So the idea is this. You want to take the limit, and if you know it's geometric, then you just jump right into what we were doing. But if you're just looking at a general series here and it's not geometric, you want to take this thing here we call a sub n. And plugging in each number gives us the list of numbers in the sequence, and then we sum them together to get the series. Well, if we take the limit as n goes to infinity of a sub n, so this is really the limit of the numbers in the sequence. This is not the series right now. This is a huge distinction. Imagine I plug in 1, I plug in 2, I plug in 3, and then I separate those numbers by commas. And I just see, well, where do those numbers get closer to? So let me just do that real quick. So if I plug in 1, I get 3 over, oh no, I get 0. Well, that's not good. So we're going to have to start this at 2. Okay? That really won't affect it. So if I plug in 2, I get 5 over 3. And then the next term when I plug in 3, I'm going to get 7 over 6. And let me just do one more. If I plug in 4, this should go up to 9. And this one should also be 9. So I get 1. And it'll go on and on and on. I'm not adding them together in this one. What I'm doing is I'm saying, well, what number, what value are they getting, are the numbers in the sequence getting closer to? Well, this is just a pretty basic limit. My degree of the top and the bottom are the same, so I just divide the leading coefficient, so I get 2/3. So what I want you to picture is at the end, I understand there is no end. It goes to infinity. But towards, in the millions and billions, and that's nothing compared to infinity. But just imagine that somehow there is towards the end of this. You're just going to picture a bunch of 2/3, right? You're going to picture a bunch of numbers that are so close to 2/3 that we can just round them to 2/3. So if you add 2/3 and then another 2/3 and then another 2/3, if you just do that forever, there's going to be no wall. It's just going to keep going forever. So the nth term test says this: if this limit equals anything other than 0, then it diverges. So this diverges. Now, what is super important is you want to look at this first, because if this happens, it's the least amount of work that you'll have to do on a problem. You should be able to evaluate limits pretty quickly, and if you see that the limit does not go to 0, you're done. You just say it diverges. If it does go to 0, you cannot say that it converges, or else this video would end right now, and that's all we would have to do. We would just do this every time and we'd be done, but that's not what happens. If you get a number other than 0, it has no chance of converging, because you're adding this value that's not 0 at the end over and over and over again, and it's just going to keep going. Now, if this goes to 0, it means you're adding these tiny, tiny numbers at the end. It has a chance of converging. Some of them will converge and some of them will still diverge, which is where we're about to go into a plethora of all these different tests that we're about to go over. So it's, again, really important that the nth term test we understand. If you take the limit of the sequence, the a sub n that generates the sequence of terms, if that does not go to 0, you're done. It diverges. Now, it's not going to happen most of the time, because then that would just be too easy. If it goes to 0, it does not mean that it converges. That's not how logic works. It means that it may converge. Then it's like proceed to all these tests that we're about to talk about. All right, let's move on. All right, on we go. So now we're going to take a look at the integral test and p-series, and we're going to start to build different ways, again, to take a look at how to determine whether a series converges or diverges. So if you just look at these two, and actually these two also, all 4 of them, the first thing you want to do is just try the nth term test. They're not going to work. If they worked, then I would be done, right? Again, like most of the time it won't work, but on the time that it does, it's going to save you a lot of time. So always just look at a problem and say, okay, if I just take the limit as n goes to infinity, right, of the terms that are in the sequence, where do those terms tend towards? Well, every one of these is 1 over infinity, which is 0. So they're all good. They all go to 0. Now, that doesn't mean that they converge automatically. It means that they may converge. They pass the first level. We can't say they diverge right away. We're going to keep going with it. So what we have is the integral test. All right. The integral test is if you had 3 things. So if the function is continuous, it's always positive. And when I say function, I mean like the a sub n, and it's decreasing. So these 3 things hold, which if we look at this, and this one too, they are continuous from this one 1 to infinity and this one 2 to infinity. This is certainly discontinuous when n is 0 or 1, right? But starting at 2, it is continuous. This one is not continuous at -4, but we're starting at 1. All right, so it's continuous on the end from n equals whatever its first index is all the way to infinity. They're both positive because I'm only plugging in positive numbers, and there's no negatives anywhere in sight. And they're both decreasing. If you have 1 over and you just keep making n bigger and bigger numbers, 1 divided by a bigger number is getting smaller. So it satisfies those three things. What it says, the integral test, and I'm just going to do these examples, but the integral test just says, we'll take the integral from 2 to infinity, but I'm going to write it as r and then take the limit as r goes to infinity. If you remember when we did improper integrals of this function, I'm going to write it as x's. It doesn't really matter, but dx just, I don't know, dn just kind of looks a little bit different, and we might be more familiar with the x's. So now we have a problem, right? So what happens is we're going to do this. And it turns out that if that converges, then the series also converges. And if that diverges, then the series also diverges. All right, so these things are very, very linked to each other. So just you figure this out instead of this, and then this informs this answer. This is a u substitution. So for this one, I'm going to make u ln x, and du is 1 over x dx. This works out perfectly. I've got a 1 over x dx here. So I have the integral of 1 over u squared, which is u to the -2 du. I know I have a limit from 2 to r, but instead of plugging in this time, I'm just going to do this real quick. The integral of this is u to the -1 over -1, so it's -1 over u. But u is ln x, so I'm going to get -1 over ln x. That's going to be evaluated. Now that I put the x's back in, I can use the 2 to r. I'm probably notationally kind of taking some shortcuts here, but I just found this to be easier to do it this way. Now we plug in r, so I got the limit as r goes to infinity of -1 over ln r minus a negative, so plus 1 over the ln of 2. What happens here is this limit goes to 0. It's 1 over infinity. Then this is a constant, so this is the answer. So since we get a constant value, then that means that the improper integral converges, which means that the series also converges. What's super important is that the integral goes to this value, whatever 1 over natural log of 2 is, but this does not go to the same value. It actually would go to a value that's smaller than that, but you're not asked to find that value because we wouldn't be able to find that exactly. So all we have to do is if we get a number here, then that means that this converges. All right. Let's look at one more example like this. So again, this satisfies all three of these. So I'm going to do the limit as r goes to infinity, the integral from 1 to r of this function with x in there. But that's really just x plus 4 to the -1/2 dx. If I add 1, I get 1/2. And if I divide by a half, I get 2. So I get 2x plus 4 to the 1/2, evaluated from 1 to r, and that's the limit as r goes to infinity. So if I plug in r, I get the limit as r goes to infinity of 2 times r plus 4 to the half, minus, if I plug in 1, I get 2√5. Now this one, this limit, that goes to infinity. That's just infinity to the half. That still just grows without bound. And I subtract 2√5, and that's still going to infinity. So that means that this improper integral diverges, which also means that the series diverges. So essentially, if you can just take the integral of this on the interval 1 to, or whatever number's here, to infinity, and then you do the improper integral using limits, if that converges, then this converges. If that diverges, then this diverges. Okay? So now let's move on to p-series. P series is basically when we have the summation, any summation of 1 over n to the p, and you get two options. P is either going to be less than 1, or it's going to be less than or equal to 1, sorry, or P is going to be greater than 1. When P is less than or equal to 1, our series diverges, and when it's greater than 1, it converges. Again, you can look up videos that explain this in a better way. It's pretty fascinating that when it's just 1 over n, which this one is, or something smaller like 1 over root n, like it's kind of like this one we saw 1 over the square root of something, it diverges. They're examples of that it gets closer to 0 at the end. It seems like you're adding these like infinitesimally small values, but they still somehow just keep trudging along and they just never hit a wall. They just go and go and go. It's pretty amazing. And then once you get past 1, there's like a switch that occurs that those values are so small that they do hit a wall and they converge to a value. So it's super simple. I have two examples here. This will take us 20 seconds. This one, n is 5. 5 is bigger than 1. So something like this automatically converges. And this one, n is 1, so it diverges. All right, this one is called the harmonic series, 1 over n, the specific type when p equals 1. It's a type P series, we would call it the harmonic series. That's an example of one. If you do 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on, if you add those up, again, you're having like 1 over a billion and 1 over a trillion. It's still, if you keep adding them, they just keep moving the needle forward. But once you switch over, if you have 1 over n to the 5th, those values will eventually hit a wall that's not very large either. They will quickly like hit a wall and then you'll just keep getting closer and closer to some value. All right, so the determining value is 1. When it's greater than 1, it converges. When it's less than or equal to 1, it diverges. So P series is going to lead into a bunch of other types of tests that we're going to use. So that's why these were so simple, but we're going to be using these within the next couple tests that we take a look at. So let's move on to those tests. All right, let's move on to two tests that are very related to each other, the direct comparison test and the limit comparison test. These two tests are very, very much related to P series, and they're related to each other. So for direct comparison tests, the way these are going to work is we're going to want to compare them to something. Most of the time you're going to compare them to a P series because P series are ones that we can know immediately whether they converge or diverge. So for instance, the way you want to do this is I'm going to compare this to 1 over n. So the way we go about comparing this is going to have a smaller denominator. And when you have a smaller denominator, you're going to have a bigger fraction. When you're dividing it by a smaller number, let's say you have something that you're dividing amongst a smaller number of people, each person's going to get a bigger chunk of whatever you're dividing up. So this is going to be bigger than this. 1 over n minus 4 will be bigger than 1 over n. And if you don't believe me, just try a couple of values. So what we know about the summation of 1 over n is that diverges. Well, if every term is bigger than every term here, and we can really just be safe to 1 greater than or equal to, but it will simply be greater than. If every term here is at least as big as that term here, then the sum of this should be bigger than that. But if this diverges, if that sum is literally going to infinity, then this would also have to go to infinity. So this also diverges. So I'm just writing 1 over n minus 4, but it's the summation that diverges. So it comes to these two critical, logical thought processes is if you have a sequence or series, or really the sequence where every term is bigger than every other term, and the second series diverges, and the first one must diverge. Anything bigger than something that diverges must also diverge. Then the opposite of that is, let's say you have a known series that converges. So that means that you have a wall, it adds up to some certain specific value. if you have a series or a sequence of terms where every term is less than that term, when you add them together, it should give you a value that's less. Well, if the first one converges, then the second one will just converge to a smaller value. And since we don't really care what that value is, all we're figuring out is, does it converge or not? We'll know that it converges. So let's take a look at that case. So we get 1 over n cubed plus 5, and I'm going to compare that to 1 over n cubed. Well, I know 1 over n cubed converges because it is a p-series where p is bigger than 1. And I also know that when I make the denominator bigger, all right, that means I'm dividing something up amongst more people, then everybody's going to get a little bit less. So this is less than this. And less than or equal to, but it's really just less than. So this has to be less than this. So if the sum of this converges, then the sum of this must also converge just to a smaller value. If term by term it's a little bit smaller, then it'll also converge. So this converges. So we're doing just something called the direct comparison test, where I'm directly comparing them. And if it's less than something that converges, that converges. If it's greater than something that diverges, that diverges. Well, there's really 4 possibilities if you think about it, right? What about less than diverging or greater than converging? Well, they are, by the direct comparison, inconclusive, because if it's greater than if it's greater than converging, it could converge to a larger value, or it could also just go to infinity. And if it's less than something that diverges, it could also diverge. It should just go to infinity a little bit slower, or it could just converge. So those other 2 are inconclusive. So when you get these 2 cases, direct comparison works great. When you get the other 2 cases, then you might want to do what's called the limit comparison test. Now, again, there are other videos if you just want to search limit comparison test. All I want to go over is like the main case for the limit comparison test. There are other like smaller cases that may show up, but most likely I'm going over like the most common part of the limit comparison test. So here's how you can think of it. Again, this isn't the entire limit comparison test, but this is the main like thesis of it that I think as a student, if you think of it this way, it's going to be really useful. So what you want to do is, for both of these, you're going to take the limit as n goes to infinity of a sub n over b sub n. A sub n is just known to be the one that's in here. B sub n we're going to come up with. And again, here is the thing. If you do that and you just get a positive number, any positive number that's not infinity and that's not 0, any other number is good, then that means that these series do the same thing. So it's really important that you know when you choose your b sub n what that does, because getting a limit of, like, say 2 in some cases could mean diverging, and in other cases could mean converging. And that's going to get really tricky later when we do the ratio test, and there is a definitive, like, if it's this number, then it's this, and if it's that, then it's that. Here, the number we get isn't indicative of if it converges or diverges. What is happening is if you get a positive number as your limit, these do the same thing. So it's really dependent upon what b sub n does. So when you choose your b sub n, you have to know what it does. But we're going to choose our b sub n to be a p-series, so we're going to know exactly what it does. So for this first one, you're going to take the limit as n goes to infinity of a sub n over b sub n. Well, the b sub n that I want to choose is typically, if you just look at the difference in degrees, well, this is degree 0 and this is degree 2. The difference in degrees is 2, so use that p-series. So I'm going to choose my b sub n to be 1 over n squared. And I'm going to note down here to myself that this definitely converges because p is greater than 1. So I know this converges. So if I get a numerical value then that means these do the same thing. So that will mean that this one, too, will also converge. Well, I just do a little bit of dividing by the reciprocal. That's going to flip this n squared up. I'm going to get n squared over n squared minus 4. And it's going to work out perfectly that I get 1. 1 is a positive number. That means these do the same thing. Since this one converges, this one also converges. Okay. Now, two things. If we tried to do the direct comparison test, it would not have worked because this is actually bigger than the one we'd be comparing it to. So bigger than converging is, again, inconclusive. The second note is it is possible to get 0 or infinity, and we can still figure things out from there, but they're very, very specific cases. Again, I'm going over for the limit comparison test, just the general case. Do the limit, get a positive number, that means they do the same thing. So let's take a look at how that works for number 2. I'm going to do the limit as n goes to infinity of 3n squared plus 2n over 4n cubed minus 5. Now I have to choose my b sub n. I choose my b sub n based on the difference of degrees. They have a difference of degree of 1, so I'm going to choose a p series of 1, which is 1 over n to the first, which is just a harmonic series, 1 over n. And I'm going to note that 1 over n diverges. We talked about that earlier. So therefore, I get the limit as n goes to infinity. I'm going to divide this. N's going to come up and distribute up here to give me 3n cubed plus 2n squared over 4n cubed minus 5. That gives me a value of 3/4. Oh, I get a number. I get a numerical value. So it must converge, right? But no, because again, there's going to be a test later that does tell us that if we get a number less than 1, it converges. We have to keep these tests separate. Just because I get a numerical value doesn't mean that things converge, like it did back with the integral test. Or later when we fast forward, or I'm sure you've heard of the ratio test before. So the idea is all these tests, we have to keep them separate, and we have to know exactly what that test is telling us. So what 3/4 tells us is that, okay, it's a positive number, good. A sub n and b sub n do the same thing. Well, b sub n diverges, so that means our original diverges. So I picked these examples because both of them give us a numerical value, but one of them is converging and the other one's diverging. So again, getting a numerical value, a positive numerical value for the limit just tells us that a sub n and b sub n do the same thing. So you have to know what b sub n does. So I would suggest when you put it down here, writing down, does it converge, does it diverge? So then I know, okay, I got a number, so diverges is the answer. Or I got a numerical value, converging is the answer. Okay, let's keep going. All right, let's keep it going. So we take a look now at the alternating series test. This one can be a little bit, it's pretty straightforward, but it can be, it's meaning that there's not like a lot to do. It can just get a little confusing with now what we call a sub n. So we had been calling a sub n the whole thing, but now when we have this like alternating factor, I guess we could call it, when usually you're going to see it as -1 to the n, all that's going to do is all, with -1 to the first is -1, but -1 to squared or to the fourth or to any even powers may be +1. It's going to create this alternating series, so positive, negative, and so on. But what we do with these is we think of the a sub n. The a sub n is really just this term. And then we have a -1 to the n. So we really think of it as -1 to the n times a sub n. So what I do is I only think about a sub n right now, not the alternating parts, so like the non-alternating, so as if they were all positive. If the limit of that goes to 0, that sounds familiar, right? That's related to our nth term test. If that doesn't go to 0, then we're done. It diverges. But if we need that to go to 0, and then we need that to be decreasing, right? If you put the alternating part to that, that doesn't really make any sense. So that's why we have to only be looking at, we have to ignore the alternating part, and we have to say, is that decreasing? Well, this one certainly is. If you make n bigger and bigger and bigger, bigger denominators mean you're going to get smaller and smaller and smaller. So if the positive part of it, if we get rid of the alternating factor, if that part of it goes to 0, which it really would have had to have done already, because if it didn't, we would just be done by the end term test and we would just say, this diverges. And if that's decreasing, what that means is that the alternating series converges. So this converges because the non-alternating part of it goes to 0 and is decreasing. That does not mean, we will talk later about conditional and absolute convergence, but that this criteria does not mean that this converges. All right, if you had just this by itself and not this, this actually would diverge. This is more related to the harmonic series. All right, so it's saying that if these things are true about A sub n, then the alternating version of A sub n converges. I hope that helps. We'll revisit that at the end when we do absolute and conditional convergence. So then what happens is we have this thing called we start to build called an error bound. We'll spend a lot more time on this in part 2, but I just wanted to introduce this idea. So imagine that what this series would look like. So if you plug in 0, you're going to get 1. If you plug in 1, you're going to get minus a half. If you plug in 2, you're going to get plus a fourth, then minus an eighth, then plus a 16th, then minus 1/32, and then you're going to go on and on and on forever. All those powers of 2 on the bottom. At some point, I could just chop this off. So first of all, I know it's going to converge because it's geometric and r is between -1 and 1. So I know it's going to converge to a value, and I could certainly find that value. But what if I just decide to chop it off? Let's say right here. All right, so this represents the summation from 0, 0, 1, 2, 3 of -1/2 to the n. All right. So that equals that value. We don't need to know what number that is, but right, that's just some number. And then there's also a value that all this adds up to. And we could actually find it for this because it's geometric, but sometimes you can't. So we obviously could just find those and subtract those values. So what happens is there's going to be an error. If we use this to approximate the whole sum, it could be pretty accurate, but it's going to be off. That amount that it's off is what we call the error bound. And what we're trying to do is figure out, well, what's the bound on that error? What's the most that it could be off? And it turns out that the most that it can be off is the first unused term, really the absolute value of the first unused term. So in this case, it'd be 1/16. And the idea is this. If we stop here, then we're some distance away from, let's picture this being a wall. So the wall is where we would go, if we go forever, there's this wall at a number that we never reach. We get really, really, really close, but we never reach it. So basically what happens is if we stop here, wherever we are, the distance to that wall is essentially our error. So now we add 1/16. So we go 1/16, and now we go back 1/32, right? So basically, now that we go back 1/32, then the wall must be closer than 1/16, because 1/16 must put us. And it's also important to note that I explained it with this wall. When it's an alternating series, it goes on both sides of the wall. It goes past the wall and then on this side of the wall, and then it just keeps getting closer to the wall. So that might have been confusing when I was explaining it. But the idea is that 1/16 puts us a little bit past the wall, and then the 1/32, we subtract it, it brings us back, and then we'll have 1/64. So the idea is that the 1/16 is the furthest that we could ever be from the wall, because the amount that we come back is going to be less than 1/16, because the A sub n values are getting smaller and smaller and smaller. So basically, then however far we are, then we are going to now add back 1/64, which is going to be even less. So the idea is the furthest away we can ever be from that wall is 1/16, because every value will be alternating back and forth, and we'll never make it back. So I'm not sure if that made any sense, but at least hopefully, if not, then find another video that explains just this topic, and I'm sure they'll do a much better job of explaining that. But for what we need to know is the first unused term is the error bound. So if you just look at a quick example, here we're only looking from 1 to 4, so it wants to know what is the error bound. Basically, how close is this? How close is this to the infinite series? And we can just say that the error bound is less than or equal to, well, the first unused term would be substituting in 5, but it's really going to be the absolute value. So if I plug in 5, I'm going to get -1 to the 5th, right? And then I get 1 plus 25 is times 26 over 5 to the 6th plus 6. I did not figure that out, so I will just go to the calculator. 5 to the 6th plus 6 is 15,631, which means our error bound is the -1 goes away because it's absolute value, so it's 26 divided by that, and it is about 0.0017. So that means one more time at this, if you add this up to infinity, you will have some wall, right? That you have some value that it's converging to. And if you just stop after the first 4 terms, we're pretty much saying, well, how accurate is that to what this actual wall is? And it's saying that we are definitely within 0.0017 of the actual answer. It doesn't mean that we're exactly, it just means we are within that, so something less than that. So then later you'll see we'll be able to we'll be able to figure out how accurate something is, and we'll be able to get more accurate if we essentially, carry out more terms. We'll get closer and closer to what the infinite answer is. Okay? All right, we have one more kind of group of topics to go over. All right, let's move on to our last couple problems. So we're going to take a look at the ratio test. The ratio test says this: if you take the limit as n goes to infinity of a sub n plus 1 over a sub n, the absolute value of that, and that equals some value. If that value is less than 1, then the original a sub n converges. If that value equals 1, then it's just inconclusive and we have to use another test. If it's bigger than 1, then it diverges. So again, it's important to know what these numbers that we're getting for the limits, what they actually tell us within that test, because they could get confusing. If you confuse the tests, then we saw earlier, getting 2/3 meant diverging and getting 1 meant converging. Well, here if we got 2/3, it would converge, and if we got 1, it would be inconclusive. So it's really important to know within which test what the criteria is. So let's just see how this works. So for number 1, we are going to do the limit as n goes to infinity of a sub n plus 1. That just means we replace each n with n plus 1. So we get 2 to the n plus 1 over n plus 1 factorial. That's the absolute value. And what happens is I'm going to divide by a sub n. But that's just multiplying. Most of the time it's going to be a fraction. So it's multiplying by the reciprocal. So that's n factorial over 2 to the n. So now this is the limit as n goes to infinity. Well, 2 to the n plus 1 over 2 to the n, if you subtract the exponents, n plus 1 minus n is just 1. So that's really just 2. And an n factorial over n plus 1 factorial, one way to look at that is n factorial. N plus 1 factorial is really n plus 1 times n factorial, because it's 6 factorial is really 6 times 5 times 4 times 3 times 2 times 1, which is really 6 times 5 factorial. So then the n factorials are going to cancel, and you're just going to be left with n plus 1 on the bottom. And if we take that limit, then that's going to be 2 over infinity, which is 0. 0 is less than 1, so this original one converges. And one more example. So we do the limit as n goes to infinity of the absolute value of 2 to the n plus 1 over n plus 1, then times the reciprocal of this. That's the dividing of that's dividing by this, which is multiplying by the reciprocal. So n over 2 to the n. Again, at least for these problems, like we know that the n's are positive and it's not alternating, so the absolute value is not really necessary at this point. 2 to the n plus 1 over 2 to the n we just saw is 2. Then we just have n over n plus 1. And what that limit turns out to be is 2. So 2 is bigger than 1, so this one diverges. All right, let's move on to our last two problems. All right, now we take a look at our last two problems. So this is absolute versus conditional convergence. So something that converges absolutely means most of these are just in regards to alternating series. So if you have an alternating series and if it converges, if you took the alternating part away, you basically took the absolute value of it. If that converges, then we say it converges absolutely. Because if that converges, that means when you add all the values up, there's a wall that it reaches. Then if you go through and you make every other term negative, well, then you're going to take away from that wall. So that alternating series will also converge just to a smaller value. So what we do is we basically can just say, all right, if it's alternating, what we can do is we can just say, well, does it converge absolutely? Meaning both the a sub n and then the negative 1 to the n a sub n converge? Or does the alternating converge, but the absolute value of it diverges? That's what conditional convergence is. So if we take a look, what we want to do first is just take a look at the summation of a sub n. And if we do that, we get this. Well, this is essentially just a p series, or really it's the harmonic series multiplied by 3. Well, if the harmonic series diverges and we multiply return by 3, that's also going to diverge. So this diverges. Now this is important. This is just the a sub n. This is just all the positive numbers. So that diverges. But maybe if I make every other term negative, that'll take away enough that it will now converge to some wall or some value. So let's see what happens. Well, if we just look at this, if we put the alternator back in, what happens is this is the alternating series test. This certainly tends to 0. The a sub n part certainly is decreasing. So therefore, by the alternating series test, this part converges. So since the alternating version converges, but the absolute value version diverges, we say that that converges conditionally. All right, so basically you have this a sub n, and you think of it, that a sub n could just be itself, or you could attach an alternator to it so that it alternates. And converging conditionally means it converges on the condition that it's alternating. The regular version does not. Then what also can happen is, let's get rid of the alternating part. I'm just make it 2n plus 3 over 6n cubed minus 5n. We're just going to look at that first. So this is one where I would do the limit comparison test. So I would do the limit as n goes to infinity of 2n plus 3 over 6n cubed minus 5n. And I would divide it by 1 over n squared, because n squared, or degree 2, is the difference between the degrees. That's going to flip up. It's going to give me the limit as n goes to infinity of 2n cubed plus 3n squared over 6n cubed minus 5n. That's 2 over 6, which is 1/3. So since I get a numerical value, again, the limit comparison test tells me that these do the same thing. And I should have done this. 1 over n squared, I know converges. So that means that this converges. Because again, I got a positive numerical value, which means they do the same thing. Since this is a p-series that converges, this also converges. That means I'm done because the absolute value of it converges. So then I would say this converges. I would say it even more strongly. It converges absolutely. It absolutely converges. I don't have to check the alternating. It must converge. If all the positive values converge, if the a sub n converges, and then I go through and I make every other term negative, well, then I'm just like subtracting a bunch from that. So it's going to also converge just to a smaller value. So that's the difference between something that converges conditionally and something that converges absolutely. It's possible that the alternating version just diverges, and then it's just diverging. So there's really 3 possibilities: diverging, converging conditionally, or converging absolutely. So that brings us to the end of part 1. Stay tuned. There's one more video, and that will be on part 2, where we'll dive into power series and Taylor and Maclaurin and all of that good stuff, which is basically the second half of this unit. All right. So as always, like this video, subscribe to our YouTube channel, check out our Patreon, definitely check out TikTok, Instagram, and Facebook, where there will be a bunch of problems that we post each day related to the topics that I went over in this lecture. Hope that was helpful. Have a good day.